Hi, ladies and gentlemen. In the last class, we understood the mu and yellow combining characteristics, and we saw that these are logarithmic characteristics, so we cannot easily implement them with linear time invariant systems. So we go for a piecewise linear approximation model for these companders. That is what we see in this video. So the speech is organized into a learning outcomes overview of this and a practical A255 mu255 compounder and a practical ALO compounder and their demos. So what you will learn are you will understand the 8-bit PCM frame, then you will learn the practical implementation of MULO encoder and decoder, then you will see a demo of this implementation in Python, then you will learn the practical implementation of ALO encoder and decoder, then you will observe the demo of ALO encoder and decoder with Python. As I said, the logarithmic characteristic is approximated to a linear model, a piecewise linear model. How do we do that? I take 8 line segments in the positive direction and 8 line segments in the negative direction. The center one is contiguous, so there are 15 segments, and each segment, these segments have a decreasing slope as we go in the positive direction or negative direction. So that will approximate our yellow or mulo characteristics. So the structure of 8-bit PCM frame is this. I have got 8 bits, of which one is a sign bit and 7 bits are the magnitude. So the first bit is a polarity bit. If this polarity bit is a 0, it is a positive. Is a 1, it's a negative. And the next 3 are segments, because I have 8 segments in the positive direction and 8 segments in the negative direction. So they are represented by 3 bits. So this represents my segment number. Now within each segment, the value is quantized to 16 levels. There are 16 quantization levels in each segment. So those 16 quantization levels are represented by 4 bits. These are the quantization levels. The first LSB 4 bits are the quantization levels. The next 3 bits are the my segment number, and then the polarity, whether it is positive or negative. Now in a mu255 compounder, the polarity bit is chosen as if the sample is positive, it is a 0 sample. If the sample is negative, it is a 1. Once a polarity is identified, the segment is to be identified. So there are 8 segments. So these 8 segments are identified the endpoints. The speech signal is divided by the whatever is coming from the microphone physical system, that is divided by its maximum value, then multiplied by 8159. The maximum value is 8159. So then values from 0 to 31 form the first segment, then 31 to 95 is the second segment, 95 to 223 is the third segment, up to 479 is the fourth segment, up to 991 is the fifth, then up to 2015, up to 4063, and the last one is 8159. From this you can see that the slope is decreasing. The slope of these curves are decreasing. So the segment is identified as the smallest endpoint that is greater than the sample value. S is equal to the smallest a such that x is less than or equal to 64 into 2 raised to a minus 33. 64 into 2 raised to a minus 33. So these values of a are from 0 to 7. These are the segment numbers. Now, once we have decided a value is given, you compute the corresponding segment number. Once you have the segment number, then there is an error between the actual value and the segment number, because the segment is a crude approximation. Then I have 16 levels in the quantization. 16 quantization levels are there. We have to ascertain which quantization level this value falls into. So for that you have to see the residual error between the sample value and the lower endpoint of the segment. So that residual error is r equal to x when s equal to 0, and it is equal to x minus 32 into 2 raised to s minus 33 for segment numbers from 1 to 7. For the middle segment, the value is the error itself, as you can think. Then for segments from 1 to 7, these are x minus 32 into 2 raised to s minus 33. So from this you can find the residual error. Once this residual error is computed, we can have the quantization level. The necessary quantization level is a 1 containing R. So Q is the smallest B such that r is less than or equal to 2b plus 1 if the segment is 0, or else it is 2 raised to s plus 1 into b plus 1 for a segments 1 to 7. Okay, then we can compute this b value will be between 0 and 15, so they can be represented by 4 bits. And once this 8 bits are ready, you can transmit them. Okay. Once you transmit them, decoding, how to decode to the original value is of prime importance. The decoding is fairly simple. The sample value is decoded from these quantization levels and segment levels as y equal to 2q plus 33 into 2 raised to s minus 33. Straightforward implementation, where these q and s are not in binary but as decimal values. So whatever 8-bit coming, the first bit that represents the sign, the next 3 are taken, converted into decimal, that is my s. Then the next 4 bits are there, converted to decimal, it is q. Then this 2q plus 33 into 2 raised to s minus 33 will give you my sample value. The first bit gives you the polarity value. So let us see this Python demo. Before going into the Python demo, this is how the table. Either you can have implementation of the algorithm I just explained, or you can go for a lookup table like this. These are the quantization endpoints, like 0 to 31. That is the first segment. Okay. There I can have quantization levels from 0, 0, 0 to 1, 1, 1. Then this is the next segment, 31 to 95, that way. This is 0, 0, 0, 0, 0, 1 up to 1, 1, 1. I have 8 segments here. Okay, and 16 quantization level within each segment. Now let us look into this code. This mu255 speech coder. So here I import the scientific computing modules and plotting modules. Then I import 2 other modules, XLRD and XLWT. They are for reading spreadsheets or Excel files, reading and writing Excel files. Why? Because my speech sample is put it in an Excel file. What I have done is, from my microphone, we have tapped the speech signal and stored in displayed in a digital storage oscilloscope, and this display that is exported to a CSV file. Okay, so that my speech sample, this is a real speech sample that comes as comes in an Excel file. It is for reading this Excel file that I use XLRD and XLWT. And then I go and implement a mu255 coder. So I define a mu255 coder x if the then the input to actual system is absolute x, because I separate the polarity. How do I separate the polarity? I separate the polarity this way. The polarity is p equal to 0.5 into 1 minus sine x. So if x is positive, this becomes a 0, because sin x is 1, so it becomes a 0. When x is negative, this is a 1, this is a minus 1, so that it becomes a 2. This 1 minus sin x becomes a 2. 2 by 2 into 0.5, it's a 1. So when the sign is negative, it is a 1, and the sign is positive, p is 0. Now then I have an intermediate value that is in plus 33 into by 64. That's a straightforward implementation for the segment number. So the segment is computed this way by logarithm, because that equation was that equation was 64. So I have to divide x plus 33 by 64 and take a logarithm with to the base 2. So the logarithm to the base 2 is computed this way by dividing by log 2. So then I take the ceiling of this, because it's upper value, then I take the integer value. If this s equal to 0, the residue is input, because here we have set that equation for the residual error. That is, if s equal to 0, the residual error is x, or else it is something else. So here I put this way, the residue is the input, the absolute value of input, or else the residual value is this minus 32 into 2 raised to s minus 33. So in this case, the b value will be the ceiling of this residue minus 1 into 0.5. Here it is else if s is not equal to 0, then it's a ceiling of residue into 2 raised to s plus 1, 1 by 2 raised to s plus 1. Okay. Then we take the binary representation for the polarity, that becomes a sign bit. The binary representation in 3 bits for S, that is a segment number, that is a second set of 3 bits, that is a segment number. Then the quantization level, that is a binary representation of the integer value of B in 4 bits. So I get this sign bit, the segment bits, and the quantization bits. This is a 1 bit, this is 3 bit, and this is a 4 bit. Now I have to join these 3 things together. This I join as a string, like I to an empty string I append this sign bit, the segment bit, and quantization bit. So it becomes my 8-bit PCM code. Now I read the speech signal from the spreadsheet. Like I use a XLRD dot open workbook speech sample new. This speech sample new is there in my hard disk and in the correct present directory. I read this, then I extract the sheet. The first sheet is extracted. It is in the first sheet. So for counter in range 2 to 2, that is in the second column, I have these values. These values I read from the third row to the 35,000 row. That is my speech signal. I will show you that spreadsheet. This is how that spreadsheet looks like. The first column is the time. Okay, the first column is the time, and right column, these are my speech values. Okay, these are my speech values. There are quite a few speech samples in that. So I read this. I read it as an array. Then I create a PCM system. To these samples, I apply this mu255 coder for every speech value. Then I multiply by 8159 so that every value is within 8159. Then I apply the mu255 coder on the speech value. For every speech sample, I apply this function here, so to get a PCM out array. Now, with this, I get my PCM signal, PCM value for each of these speech samples that I write as an array. Now decoding the PCM is straightforward. What I do is we implement that equation straight away. What is that equation? The one here. This 2q plus 33 into 2 raised to s minus 33. These binary bits are taken. Then they are the first bit is taken. This is x0 is my first bit, that is a polar sign bit. Then the next one, the segments are taken. Then interval 3 is nothing but my q. So straightforward implementation of that equation along with the sign. So that returns your decoded value. Now I apply this PCM out array. Now I am trying to decode this PCM out array. I assume that there is no noise or anything in between. So I just apply this PCM out array to this decoder. Then I make a decode sim array. Okay, I initialize a blank array and to which I append each decoded value. So this mu255 decoder is applied to each decoder input I. Okay, then these decoder values are appended to this blank array. Now I plot these values. Okay, we can appreciate this. So I will run this code. Run mu 255 space coder.py. You can see that this blue curve, that is the original speech signal, and this red curve, that is my decoded speech. You can see that they more or less they agree, but there may be small quantization errors. If I take it here or if I take it here, you can see that they more or less they agree. the decoding is correct, but because I assume no noise. But here if you look closely, you can see that at some points there are some quantization errors. Okay, there are some quantization errors. There may be small changes when we decode the speech sample. So here also you can see that there are some small changes. Okay, these are the quantization errors happening. Now if I apply some, say, if I apply that function to some values, you can appreciate this, like this is a mu255 coder. Or say 121. If I say what is the bit I'm getting a 0. The sign bit is a 0 because it's a positive value. Then I have 0 1 0. This falls in the third segment, 0 1 0 segment. Okay, the first is a 0 0 0 0 0 1, then 0 1 0. This is the third segment. Then this is the fourth quantization level, 0 0 0 0 0 1 0 1 0 0 1 1. This falls into fourth quantization level. Now if I apply the decoder to this, if I decode the value, you can see that I'm not getting 121, instead I'm getting 123, because there are slight variations. Because there are always quantization errors, so there is no exact reproduction. But these are minor changes, minor changes. This will not be perceived by the human ear. So likewise, if I say mu255 coder minus 121, you can see that everything else is same except the sign bit. Okay, it is a 1 because the value is a negative 1. So if I give a mu255 decoder with 1 here, it's minus 121. I should be getting minus 121, but there may be small changes. I get minus 123. Okay, so you can try this code, and you can appreciate how a mu255 coder works. So let me go back to my presentation. So this is how the original speech and decoded speech look like. Now when I come to an ALO compander, this is similar to a MULO compander, except that the maximum amplitude is 4096. There are 8 segments, so the endpoints in this case are 0 to 32 to 64, 128, 256, 512, 1024, 2048 and 4096. You can see that the slope is getting divided by 2. In every segment it gets divided by 2. The segment number and the quantization level are determined by this algorithm. Like the segment number S is chosen as the smallest a, such that x is less than or equal to 32 into 2 raised to a. Okay, 32 into 2 raised to a. These algorithms are nicely explained in the book Digital Telephony by Bellamy. So when a equal to 7, it becomes 32 into 2 raised to 7. 2 raised to 7 is 128, so the last value will be 4096. When it is 0, when a equal to 0, it is 32, the lowest thing. And when it is a equal to 7, it is 4096. So there are 8 segments that way. And the residue, once we fix a segment, then I have a residue in that. It is that residue you accommodate by putting the quantization levels, 16 quantization levels. So that residue after fixing S is R equal to X if the segment is 0. It is the input itself if it is a middle segment. Or else it is X minus 16 into 2 raised to S, where S is 1 to 7. There is a printing mistake in that Bellamy book by Bellamy. There it is written 16 into 2s. It is 16 into 2 raised to s. It's an unfortunate mistake in the book Bellamy. So don't follow that algorithm, just correct it. It is when the residual for segments from 1 to 7, the residual error is x minus 16 into 2 raised to s. Now, once these residue are computed, you can compute the quantization level as R is less than or equal to 2 into B plus 1 if S equal to 0, or else it is 2 raised to S into B plus 1 for segments from 1 to 7. Okay, so you can take this B and you can implement as a, this B is from 0 to 15, so you can implement as a 4-bit number. The sample value is decoded as y equal to 2q plus 1 for the segment 0th segment, and y equal to 2 raised to S into q plus 16 and a half for segments from 1 to 7. Then this can be implemented with this code. Here also I have my SciPy and PyLab, then XLRD is imported, then I have a straightforward implementation of the ALO coder. The input is the absolute value of x and the polarity is computed. Then it is the input value, the maximum absolute value is divided by 32, absolute value of the input is divided by 32. Okay, or inp by 32, whatever. If this inp equal to 0, residue is equal to inp, or else then that bits are this, the segment is 0. Okay, or else this segment is this, that is log inter divided by log 2, that is log inter to the base 2, ceiling of that. Then I compute the residue as inp minus 16 into 2 raised to S, that is x minus 16 into 2 raised to S. I compute the value of B. Then I have a binary representation for the polarity bit, the sign, the segment bit, and the quantization bits. So these three form my PCM frame. That is a sign bit 1 bit, segment 3 bit, and 4 quantization bits. Then I read the speech signal. As I said earlier, I speech the speech sample, then you multiply by 4096. Okay, then I to a blank array I append the ALO coded speech sample. Then decoding is straightforward. This ALO decoded samples are taken and passed through this ALO decoder. ALO coded samples are taken and applied to this ALO decoder. So here in ALO decoder I take the sign. Okay, the first value is taken and the sign is separated. Then if this value, if the segment is 0, it returns this value. Okay, if the segment is not 0, then I have to have this 2 raised to the quantization level, then this quantization level plus 16.5, whatever we have written here, 2q plus 1 for S equal to 0, or 2 raised to S into q plus 16 and a half, that is implemented by these equations. Then I return this value. Okay, if the segment is 0, return this, or else return this. Then we decode this. So I apply this PCM array into this decoder and decode this sample and plot along with the speech sample. So we will run this code. Now I see a small problem here. You, my students, can look through this code and see there is an overshoot coming here. Somewhere there is something is wrong. I am not able to spot it at the moment because here it shows a warning that this S has exceeded 15. I don't know how. You please go through this. That is why it is not able to represent this S value as a 3-bit binary representation. I am not able to spot it at the moment. But if you look here, everywhere else it is following it correctly. You can see the difference between the speech sample and the original speech and the decoded speech. Okay, this is how this is the effect of my quantization noise. Now in this video you understood the 8-bit PCM frame, then you learned the practical implementation of MULO encoder and decoder, then you observe the Python demo of MULO encoder and decoder. You also follow this code and make your own codes and appreciate them. You learn the practical implementation of ALO encoder and decoder, then you see the Python demo of ALO encoder and decoder on actual speech signal. And that is the end of this presentation. I thank you all.